Hi, and welcome to ITS 277, Software Assurance and File Systems. I'm Cheryl Simpson here at Great Falls College. In this chapter, we're going to be covering the CISSP Chapter 20, which is going to cover software development security. In this section, we're going to be covering systems development controls, databases and data warehouses, and knowledge-based systems. Yes, we're kind of starting the class at the end. So we're starting with software development at this point, and then we're going to go through the rest of the study guide that's necessary for this course. Let's get started. The first thing I want to show you is our roadmap. In this class, we are going to be covering software assurance, file internals, and some policy and regulations, governmental issues that go on with software assurance. But before we get started, I want to give you kind of a fundamental introduction of the software development lifecycle and attacks and malware. I assume by this point in your journey, you already kind of understand about attacks. So we're going to go through these relatively quickly because they're probably going to be a review for most of you before we get into our real software assurance of documentations and artifacts that we're going to be creating in that section. And then the internals of files. So some hardening, how the file systems are work, incident response, forensics, and investigation. We'll finish out this class with policy and then laws and regulations that you need to know, and then a little bit of certification prep just to prepare you for the CISSP exam. Our first section of 3 for this chapter is going to be systems development and controls. In here, we're going to go over the SDLC, some life cycle models, some maturity models, how we do some planning, configuration management, Devops, APIs, testing, code repositories, and then service level agreements to finish it out. So, software development. This is not a programming course. I do not expect you to write software for this course. If you know how to program, that'll make your life a little easier, but that is not required for this course. Therefore, I'm going to spend a little bit of time explaining how to develop software. If you're going to help people in this field using security to understand how to build software projects securely, you need to have at least a basic understanding of how software is developed. So we're going to go through the software development lifecycle and different ways in which we develop software. First off, a couple of general terms. Programming languages are either usually high-level or low-level. High-level languages are going to be the languages that your programmers write in, C#, C++, Python, Java, the languages you've heard of. They will generally convert into a machine language, which are bits, ones and zeros. They sometimes hit a mid-zone in the middle of being an assembly, but essentially you go from high-level down to low-level. Libraries are pieces of code that people have built that are usually available for general consumption so that you can use them. And we use things like development toolkits depending on which language we're going to be using. So if you're using Java, you might use the Java Development Toolkit, the JDK, a Software Development Toolkit, SDK, or an IDE, which is a development environment. Depending on what type of language you're going to use, you either have a compiled language or an interpreted language. Compiled languages, like Java or C or any of the C versions, will take your code and run it through a compiler. The compiler will ensure that there are no syntax errors in your code, and it will turn it into machine code. Then you will take that machine code, and that is what is distributed and run on people's computer. That machine code is written in bits, zeros and ones. It is not easy to be able to just see the code from inside of that. You can't just look at it. There are ways to decompile and to look at things inside of it, but in general, compiled code is already into bits. So we start from our basic source code, move through the compiler into machine code, and then the machine code you run on your computer's output. The other type of language is an interpreted language. This is going to be your scripting languages like JavaScript or your Python. These languages you run straight from the source code through an interpreter and directly to the output. You don't compile it in the middle, which means the code that you hand to your end user is visible. They can actually look at the code. A compiled language is safer from manipulation. A hacker cannot go into a compiled set of bits and change the code, generally. They can, but it takes a lot more effort. Whereas in an interpreted language, the user can see the code and manipulate it easier. Therefore, it's much more frequent that you would manipulate a Python or a scripting language. That being said, if you have an interpreted language, the user has the ability to see the code, which means that there's less of a chance of the developer inserting malicious code or doing something that you didn't expect them to do. You always need to check with software assurance and security both sides of this. Is the user going to be doing the problem, or is the developer going to be doing the problem? So the difference between an interpreted language and a compiled language is a big distinction to understand as we move forward. An interpreted language goes straight from the source code through the interpreter converts it into machine code, and you immediately get the output. Our next section describes object-oriented programming. A lot of programs these days are written in an object-oriented programming language, such as Java or .NET languages, C++. Understanding the way that object-oriented languages are created is going to help you to understand how the code looks so that you can be sure of developing the security features correctly when you are looking through the code. Object-oriented uses three basic concepts. The first being encapsulation. Encapsulation, I always visualize as taking all of the code and putting it into a capsule. Encapsulation. When we make objects, we attach methods or functions or attributes to that object. Once we have tested the code against that object, that code should be safe and secure, and we can move on from there. So by building and encapsulating that code, you make it safer. Next concept that we cover is inheritance. The same way that you inherit from your parents, your children inherit from you, objects inherit functionality from their parent objects. That's a concept of object-oriented programming. And the last is what we call polymorphism, or many forms. The functionality of your object can be taken on a given object and produce different results based on the attributes of that object. Therefore, if I have an animal object, and my animal is a dog, and I ask the dog to speak, the dog will say woof. If I have an animal object and that animal is a cat, and I ask the animal to speak, the cat says meow. The concept of polymorphism simply means, depending on the attributes of the object, there may be different functionality that is appropriate based on that object. When we work with object-oriented programming, we use black box abstraction. The concept of black box is, there's a big box, big black box here. All the code goes inside of the box. The user needs to know what is the input and what is the expected output. If he puts in the expected input and he gets the expected output, the testing works. Black box testing or black box abstraction means that the user doesn't need to know how the code is implemented inside of that black box. All he needs to know is what is the input I'm allowed to give it and what is the expected output. Once I have built that code and written it and compiled it and made sure that it all works, that code works. I don't have to retest it multiple times if I don't touch the code. So the concept of black box abstraction simply means the visual of input and output, and the stuff goes in the middle, and we don't care how it happens. We just know that it works. When you're writing your code, it is important to make sure that your code does not break. You don't want your code to fail. In fact, one of the ways that hackers will attack you is by making your code fail and then hoping that you leave something open or you do something to make sure that everybody can get in once it fails. Couple of different ways that we use in programming to make sure that you don't fail. First, most important, is input validation. Most hackers are easily able to get into your system by hacking through user input. If I'm going to enter in a name and I'm going to type it into a text field and hit submit, depending on what happens in the back end of the code, the hacker can enter specific pieces of information into there and actually create the hack that he wants, get into the access, be able to get into your database, be able to change your system. What we do for that is to make sure that all of the input that the user is going to enter is validated in some way. If I am asking for an age, what is your age? I can pretty much guarantee that it's somewhere between 0 and 120, maybe 130, and it's a number. It's an integer number between 0 and 130. It is not going to be a string. It is not going to be text. It's not going to be a Boolean of true or false. And it's definitely not going to be a very long string, including the word script somewhere in there. If I check my input to make sure that it only uses the values that are available, I am doing input validation. Make sure that the user entry is what you expect it to be. Sometimes you can't avoid this. I want to ask for your name, and I'm definitely not going to have a list of possible names to check against. So in those cases, we have to have more defense in depth. We have to have more options to check to make sure that we do things correctly. But if you can do input validation, it is one of the best ways to make sure that your code is safe. Our second is authentication and session management. Using multi-factor or two-factor authentication, you know, the thing where you enter a password and then it sends a text to your phone and you have to enter in your phone something you are, something you have, something you can't, something you know, something your password is something you know, something you have is your phone, something you are is your biometrics. That kind of multi-factor authentication is a great way of making sure if your password is found out, if it's out available on the dark web, then I can have at least a secondary option to be able to get into the system and to check that authentication. You also want to make sure that you have built-in security as you go along. It is built in from the very, very, very beginning. Plan on authentication, session management, input validation from the beginning of writing your code. You don't just throw it on at the end. Hey, I finished all my code. Oh, let's go make sure it's safe. If you check it every step of the way through the software development, you'll find that it works really well. The next thing we use is error handling. What happens if something goes wrong? So we're going to have a little bit more on error handling as we go along, try catch blocks and so on and so forth. But the important thing about error handling is to try to avoid your system crashing and to get it to fail appropriately, to handle the error. It also makes sense to use the details of your error message should be as minimal as possible. If you tell the hacker exactly what he's doing wrong, it's easy for him to fix it. Oh, I'm getting the password wrong. I'm going to keep the same username and enter in a different password. When there is a failure, we want to log it, document every failure that you have. Make sure that if you had any input validation errors or authentication attempts that failed, session tokens that are failing, administrator privileges, make sure that you log all of those. So you can always go back and look and see whether or not someone's trying to break into your system. And the last part about this slide is going to be your fail safe versus your fail open. We almost always want to fail safe. If the system crashes, if we fail, lock everything down. Sometimes you want to fail open because you're balancing user ease of use functionality with security. Sometimes if the failure occurs, open everything up. The example for this is if you're in a building and we have door locks to make sure that nobody bad can get into the building and there's a fire in the building. I want all those locks to open. I want everybody to be able to get out of the building. That would be a fail open. The visualization of everything is open, you can all get out. Fail safe means all the doors lock down and everybody inside gets burned up by the building. We like to avoid that if it's something like life or death. Be careful because in some cases, your software is something like controlling the door locks in a building. If there's a failure, do you want the building to lock down or do you want the building to open up? So this is fail safe versus fail open. We're now going to discuss secure development lifecycle, or sometimes software development lifecycle, or even systems development lifecycle. When you make a new project, you have to have a lifecycle that gets you from the beginning to the end of the project. And when you have it planned, it works a lot better. There are 8 essential sections of the SDLC. First, we start with, what are we going to do? The conceptual design. At this step, you need to think about how are you going to implement security into your program when you build it? How are people going to be able to use it? And what do we need to do at that step? The next is the requirement step. How do we know that we did it correctly if we don't have a list that tells us this is all the things it's supposed to do? So if we are supposed to control invoicing coming in and out of a system and we get to the entire end of a project and we never actually implemented the invoicing, we probably didn't do it right. So requirements, what does it need to do to be correct? The control specification, Who has the control over what? Who gets to do what in this program? Is it open to everybody? Is it open to only specific groups? How are we doing our control specification? Then we go through a design review and we actually design it and document and write out the algorithms of how things are going to be done. Finally, we start actually writing the code, which is why programmers are a very actual small part of the SDLC. The coding part is the actual implementation of how do you write the code. Then we get to the code review, where we look at the individual code, every line by line of the code, and make sure we implemented it the way we think we did. Do we have anything random in there where like, oh, look, if your age is 42, you automatically get an extra $100 or something like that? I mean, did we do weird things like that? Check the code, make sure the code is safe and secure. Finally, we run through a systems test, make sure that the input and the output does exactly what it's supposed to do and nothing else. And then finally, we need to keep it going, our maintenance, review, keep going, up until the next version where we make a new project and we go back to conceptual again. It's a circle. It goes around and around. You need to understand these 8 sections of the SDLC for your homework assignment for this chapter. Once we understand, okay, we're going to make a new project, we need to decide how are we going to build it. And there are 3 kind of modes of models for how we build projects. Originally, a lot of people had the basic waterfall, which was start with your design, do your requirements, finish out your design, make sure you design the whole thing perfectly, then go write the code, then test it, and then turn it in. Well, that sounds lovely, except in the real world, that doesn't really work very well. So we created an iterative waterfall, which is you start by designing things, and then every step you have the ability to take the feedback from the next step and go back and redo the previous step. So we call it an iterative waterfall because we're kind of starting the requirements, then starting on the software requirements and realizing we forgot something in the system requirement. Okay, let's go fix that, come back and try it again. Then we're in the preliminary design and we get down to the detailed design and realize we forgot something, so we go back up to the preliminary design. Iterative waterfall only goes back 1 step, and there are 7 steps in an iterative waterfall. So from system requirements to software requirements, then we have our preliminary design and our detailed design. Then we actually write our code, debug it, test it, and then put it into operations. 7 steps. But with the iterative, you're allowed to go back 1 step at a time to make sure that the feedback from the future step is implemented into the feedback, and we can keep going around that way. Another way that we found was to do a spiral where we build it in phases. We build very small amounts at a time and we build a phase of it. In each phase, you determine the objectives and the constraints. You evaluate and identify and resolve your risks. Then we develop and verify the next level project. Then we plan the next phase. Then we go do it again and we go at it again. So each time you get to a product that is not everything, but it is a single phase of that product. Similar to that is a more common version called Agile or iterative design. With iterative design, you are customer specific, delivering the software as fast as you can to the customer as often as possible. We call these sprints. We design, develop, test, implement, release, and then hand it back to the client while we start working on the next one. We build it in sections of minimal viable product. What is the most important thing to the client? Build that first. Give him just that. When you finish that, take the feedback from him and build the next step and build the next step. And we follow the sprints. Very similar to the spirals, but Agile and iterative is very customer specific. It is customer focused. We want to have customer satisfaction above and beyond. We want to make sure that the business partners are working with us throughout the product development with Agile and iterative. Sometimes with both iterative waterfall and spiral, if you don't include the business partners and the end users at the beginning, or at least throughout, you end up producing a product that isn't what they wanted. With Agile and iterative, you always keep that customer in mind and he's always part of your development team. So those were our life cycle models. We also have the concept of maturity models, and there are 3 maturity models that we are going to cover. Maturity models is a nice defined way of describing what is your software process. How are you doing this? And are you doing it to the best of your ability? Are you doing everything that you can to make your software as secure as possible? So we start with our CMN, our capability Maturity Model, CMM. The Capability Maturity Model was developed by the Software Engineering Institute at Carnegie Mellon, SEI, and they came up with these 5 descriptions of how is your software development process. So we start with number 1, initial, disorganized, little to no process. This is those hackers that say, I'm going to go write some software, and then they go and they just start writing it, but they have no documentation, they have no organization, they have no lifecycle management, they just go write the software. Sometimes that works. In a business world, it doesn't, because in a business world, we almost always need to have some version of software development process. So then we get to the second tier of repeatable. You have at least some lifecycle management, some reuse of code. We start introducing quality assurance and project planning. A lot of companies are at this stage. They think they're doing okay because there is some documentation, but there's a whole lot better they could be doing. At third level, defined, we start making formal documentation, which is part of what I'm going to have you guys do in this class, is to create some formal documentation to define your definitions, your training, your program, your peer reviews, things like that. They're all going to be defined and documented. The next one is managed, and with managed, we actually have quantitative numbers, measurement that determines whether or not we're on task, on time, is our product doing what it's supposed to be doing. We have a quality management team that is going to come in and determine, is our product the best product it can be? And then finally, the best, quote unquote, option for a maturity model would be optimized. In your optimized capability, you are actually taking your feedback from every project and using it to make sure that your future products are better. So we're going to be doing a lot of reflection, making sure that we understood what worked well, what didn't go well, how can we make it better next time. We want to prevent defects. We want to handle change management as we move along. So as far as maturity models, the capability maturity model leads you from having no software process to a completely defined, optimized, organized software process. The second maturity model we're going to cover is the Software Assurance Maturity Model, the SAMM. They were created by OWASP, which is the Open Web Application Security Project, which is a security conglomerate of consortium of interested parties that came together and said, okay, the CMM was fine. However, let's look at this from a large company point of view and what we can do to really ensure that our software is taken very well and controlled with governance and design and implementation. Instead of breaking it into a 1 through 5 maturity model, the SAM assurance model is going to break it up into different columns. So we're going to look at each thing a little bit differently. We're going to first start with governance. How is it managed? Do you have strategy? Do you have metrics? Do you have numbers that actually give you descriptions of what you are doing well, what you can improve? Our policy and compliance. And again, our training and awareness. This is all governance. How are things governed or managed throughout the process? Then we have the column of design, defining the requirements, looking at the threat assessments, looking at the architecture to make sure that it's safe. Third is our implementation. This is where our programmers are. The secure build and deployment, and making sure that if there's anything wrong, bug tracking, that's managed and controlled and metriced, so that if we do have software that tends to be more defective, we know why and we figure out how to fix it for the future. Our fourth, or the green column here, is verification, making sure that it's analyzed and requirements driven. So what is it we wanted to do? Did we do it? Is it safe? Is it secure? This is all of the testing section. And then finally, we have our operations model, which runs into our incident and operational management, our environmental management, making sure that our configurations are set up correctly, making sure that the software and the hardware work well together, and making sure in case anything bad happens, that it gets handled appropriately with incident response. So again, while the CMM, the Capability Management Maturity Model, goes through and says either you're doing nothing or you're doing everything and somewhere in between, the Software Assurance Maturity Model breaks it down into 5 different subsections and then has each one of those follow specific maturity practices. The last maturity model we're going to cover is the IDEAL, which is an acronym. It starts with initiating, which is starting out, why are we doing this? How are we going to pay for it? Who's going to be in charge? Then we get into diagnosing. Why do we need this? What's wrong with our system? And how can we figure out how to make our current system better? Analyze it, find the needs, find the pain points. The establishing is going to develop how are we going to do it, developing the course of action, creating the solution, so on and so forth. And then finally, fourth, we get into acting. This is actually the coding part of your maturity model to actually implement the solution, change it, do pilot tests, however we want to do that. And then our last section is our learning. You'll notice all of these maturity models handle, we finished the code, we handed it off, and now we have to do something about it. Think about how did it work, what went well, did the goals get achieved, and do we need to start again? Do we need to go back to diagnosing and find what are the problems with our current system and how do we fix them? The IDEAL model follows this kind of circular model of kind of an iterative design that follows the initiating, diagnosing, establishing, acting, and learning. So both the IDEAL maturity model and the capability maturity model technically have 5 sections. All 3 maturity models go kind of down a different road. Being able to recognize which model your company is using and how you can implement that in a secure and safe way is part of your job in software assurance. And that pulls us to planning. Being able to understand the basics of planning is really an important part of software development. The 2 charts I have here, first is a Gantt chart, which is not an acronym, it's actually named after a person, which is a bar chart that relates the project tasks and scheduling. It is all about making sure things happen on time. Sometimes you have certain tasks that have to happen after another task has occurred. Sometimes you have tasks that can happen at the same time. With a Gantt chart, you're able to visualize what is happening in each week. So scheduling, timing associated with the individual tasks, and when does it all become available and get implemented? Can we see the end in sight? A PERT chart is a program evaluation review technique that is the relationship between tasks. It's not as much about timing as it is about the individual tasks and how long they need to take and what can be done simultaneously. How can we parallel here? Well, we can do some hardware installation at the same time that we're doing our programming. We can do our testing at the same time we're writing our manuals. We can test our system at the same time we're training. What are things that can occur at the same timing so that we can use the option of doing things at the same time to help our schedule go along a little faster? Once your software is finished, we talk about change in configuration management because very, very rarely is software perfect the first time it gets implemented. Most of the time we have to fix things or we have to change things. So when we talk about change management, there are 3 steps to change management, and then we'll talk about configuration management. Change management follows the steps of requesting control, changing control, and then releasing control. These are things for new features and for bug fixes. When we request control in this step, we prioritize our request. Someone says, we need to change the color from red to blue. Okay, how important is that? It's about a 2 out of 10. Okay, we can push that to later. Everybody kind of puts together all of the different things that they need to do, and then we prioritize them. What's the most important thing? Well, when I type in a name, it turns everything to goober. It's probably a problem. We need to fix that now. Fast, high priority. Then for change control section, once we've prioritized all of our changes, we have them in list. Now we recreate the issue and analyze the appropriate changes, make the changes in the code. So we now have control over this section. We're going to change it. We're going to fix it. And then we're going to implement those changes. Finally, we get to the release control, which is where somebody other than the developer should be approving the release. Did you fix it? Can I check? Check the code changes to make sure that you haven't broken anything else and release the control back. We finish the change management. So change management needs to follow a subset of steps from point to A to point B. For configuration management, this is one of the more dangerous places for software assurance, so for a system analyst to go into. You need to change something, and there are different ways to make sure that your configuration management is appropriately applied. First, we do configuration identification. What's the thing that needs to be changed? I need to change this configuration from saying that only admins can have it to admins and managers can have it. Okay, we've identified the configuration that needs to be changed. We control it, make sure that only approved and tested changes are made. If I need to run this update, I need to make sure that's approved. Is this update safe? Is it tested to make sure that it's not going to break anything else? Do we have authorization to do this? So in the configuration control, we control what configurations actually are changed. Configuration status accounting is the formalized procedure and documentation of the change. You have to write it down somewhere, every single configuration change you made. Because if it turns out you did break something, we need to know what you changed so we can go back and undo it and fix it. What was it before and what is it now? A lot of times when you're trying to fix something or doing a configuration, you just start clicking buttons until you make it work. A lot of times you make it worse. You don't know what you've done, you can't undo it, now you're in trouble. And finally, we have a configuration audit, which is part of a configuration management system to check to make sure that no unauthorized or undocumented changes have occurred. You should be able to have an audit that says this is what my configuration status should be. My state for all of my configuration choices should be documented. And I should be able to go in at any point to my system and check those configurations and make sure that they are all still the same. If anything has been changed without following the regular documentation, there might be a problem. There might be a hack. There might be someone who has gone in and changed something without your permission. Our next section is on the concept of DevOps. DevOps is an abbreviation of the Development Operations and Quality Assurance trifecta. These three groups. In the real world, a lot of times you're working on a team, and in that team you have the development team, which are the software people, the people who write the code. And then you have the operations team, which are the people that are going to use the code, the end users. And then you have your quality assurance people who kind of come in and make sure that you didn't break anything in the middle and that we haven't violated any laws or rules. These three groups sometimes can argue with each other. They fight each other as they go along. From development to ops needs to do it making sure that the product works for them. But development knows how to develop. So sometimes development doesn't really care about the end user and they just develop it the way that they think is best. Then operations get really annoyed at the end because the software doesn't work the way they want it to. If we include both people in the same conversation, things work out better. Between development and QA encourages documentation of every change. Developers don't like documentation. So there is a conflict between developers and QA of, seriously, I needed to write this down. You needed to go update this document just because I made this little change. How annoying is that? And then finally, between operations and QA, the software is done. The developers finished it. The operations should be able to use it, but QA hasn't approved it yet. So ops can't use it. And then we all start arguing over, could you just finish the documentation so I can finally start using the system? This becomes an antagonistic environment. And what we do to fix it is make all three people get in the room at the same time. DevOps works with the agile iterative design to create a process that speeds up the development while still using QA security to make sure the product's secure by making sure all three parties are in every conversation. We don't have just development going off by themselves and writing software, and we don't have QA going off by themselves and writing documentation. Everybody all works together, and that's generally the concept behind DevOps. A lot of software is built with data and information in it. So if you were to build a standalone independent piece of software, then you have clients that want to be able to tap into that software, be able to get the information out of it. And those companies will now create what's called an API, an application programming interface. Things like the CDC for checking COVID information, or QuickBooks for allowing you to access your banking information. Things like this. It's an independent program, but people want to be able to access it from their own customized software. A programmer will use an API to hook into another piece of software. When you see a blog, and the blog is not on Facebook, but it has a little link up at the top corner that says link to Facebook or post to my Facebook profile, that's an API. If you have a certification and it says click here to link to LinkedIn, to have the attachment of where this certification is to your LinkedIn profile, that is an API. Social media examples are things like posting a status or following or unfollowing or liking posts. Same concept with UPS. You can have your software tap into UPS and say, where is this shipment? What is my status update? How do I get that information? So the developers build software with specific given functionality that they open to allow other people to tap into it to access data from their site. That is the concept of an API. Our next section is on testing. There are 3 different versions of testing when it comes to software. We've kind of touched on black box. White box testing is otherwise known as static testing. Static testing means all of the source code is available, and we're going to code review by going through line by line. We're analyzing the logical structure of the code. We are going to ask the developer, why did you do this? How did you do this? Why are you implementing this way? This is white box testing. We're looking at the code while we are testing it to make sure that the code does exactly what we say it should be doing. Black box testing is also known as dynamic testing. You don't see the source code at all. All you see is the user's perspective, the input, and the output, and you run through a series of input and output scenarios to make sure that the functionality works. If I'm implementing a calculator and my add button is implemented incorrectly, I might test, if you add 2 plus 2, what do you get? You get 4. Oh, well, that seems right. We should be good. No, you know what? Let's try 3 plus 5, and I get 15. And I'm like, wait, it was supposed to be adding those. That was supposed to be 8. Why is it doing 15? Oh, because the programmer somewhere in the code made a multiply instead of an add, and they need to go fix that. We call this acceptance testing. We run through a series of scenarios. There's not just one. There's usually hundreds, well, sometimes hundreds, definitely in the tens of multiple scenarios to confirm functionalities. Every time that you think something might break it, we try those functionalities. And we consider this types of final acceptance testing. When you finish all of your code and you turn it in, the software assurance team is going to go through and run final acceptance testing. Gray box testing is kind of a combination of both. They have the source code, but they test it from a user's point of view. So it's black box testing looking at the source code to ensure that we hit everything correctly. Again, if I did 2 plus 2 and I got 4, I'm assuming I got it right. But if I look at the source code while I'm doing that, I can go, wait, I'm watching the source code and I can see it's not doing it correctly. We call this validation testing. We want to validate all of our inputs to make sure that they get the correct output at the end. Our next is our code repositories and source control. So most of you have heard of GitHub. GitHub is a code repository. It's a place where you can put your code. In the real world, you have large development teams all working on the same product, and all of that code needs to be available in the same place for all of those people to access. And we put those into a source code repository, such as GitHub or Azure DevOps or SourceForge. These are places where everybody can access the code. We also implement a source control with that. Every time you make a change, we push the change up to the repo, and they're migrated and they're incorporated into everybody else's change. If I change code A and somebody else changes code B, both of those codes can go up without a problem. If both of us are working on code A, we need to look at that code and figure out if it needs to be merged. Can we merge it correctly? The code can then be identified with a key to ensure that everybody, especially development and DevOps and quality assurance, is all using the most up-to-date code each time. And our last section, or our last group of this section, is going to be our SLAs, or third-party software acquisition. So the SLA is the service level agreement. This is when you get a company that hands you a piece of software. What can I be guaranteed? Is there a guaranteed uptime? Is there a consecutive downtime that it will never be down more than 5 minutes a day? What is the peak in the average load that my company can handle or my software can handle? Are there diagnostics? Is there a failover time? Is there a time in which you guarantee if it breaks, it will be back up within that amount of time, which may be seconds, it may be minutes, it may be hours. Depends on your service level agreement. This is why companies pay for software as opposed to using free software. Free software generally doesn't come with a service level agreement. Paid software encourages this understanding relationship between you and the vendor, which is going to say, I can guarantee you your software will not fail. When you buy third-party software, commercial off the shelf or COTS, this is software that is purchased, not developed in-house. you don't have a programmer in-house writing software, you go and buy it. This is QuickBooks. This is any of the CRMs that are already out there. This is Microsoft Office. These are commercial off the shelves. All purchased software should always go through thoroughly testing before it gets installed to make sure it doesn't conflict with any of your other software. Be aware of the updates and the patches. As soon as updates and patches are available, test them against your current system and implement them as fast as possible. From a hacker point of view, they have a window of opportunity between the time that they are aware that there is a hole and the time that you implement the patch. If you wait a week or a month to implement that patch, that's a time that a hacker can get into your system. So when you buy third-party software, commercial off the shelf, you want to make sure you always test it against your current system and always update and patch as often as possible. Our next section is going to be on databases and data warehousing. We're going to cover a really quick overview of database transactions and security, how we connect to them, and a little bit of big data and some storage threats on data. So first, to understand how a database is run, there is a database management system, or a DBMS. A database management system is the actual piece of software that controls how the data is stored on the hard disk. So somewhere there is a hard disk or some disk of some type, and the data is all sitting on top of there. And the database management system knows where that data is and is able to manipulate it and manage it. The DBMS is specific to the database that you have chosen. So if you have a SQL Server database, that's a SQL Server DBMS, or Oracle or a DB2, depending on which type of database you have. There are multiple types of databases. There is a hierarchical data model, a distributed databases, relational databases, graph databases, object-oriented databases, so and so. The most common database is a relational database, an RDBMS, so a relational database management system. In an RDBMS, in a relational database, this is your SQL Server and your Oracle, Access, DB2, MySQL, all of these are relational databases. They use a primary key to identify each row in the database. There are tables, and the tables are related to each other with foreign keys. The foreign keys are used to enforce what we call referential integrity, making sure that the data is appropriate and connected correctly. If I'm going to say that I have customer ID 1 and I have invoice number 5, and invoice number 5 references customer ID 1, I need to make sure that there is a customer ID 1 somewhere that I can reference. That referential integrity, who you're referencing, that is the point of a foreign key. A primary key just identifies each row uniquely. You can't use John Doe as a primary key because there's lots of John Does out there, whereas you could have some sort of a unique identifier. Databases, relational databases, use SQL, which is structured querying language, to read and manipulate their data. They can select data from the database, they can manipulate it, they can ask for new data, they can change things, they can delete things. So SQL is the language that is used from a DBMS to be able to manipulate your data. Once the data is in your database, we like to keep it what's called normalized. It is a series of steps to ensure that we don't have any data redundancy and that the efficiency of the database is sped up. So the term normalized has nothing to do with kind of being normal in an emotional sense. It is a description of how the data is stored so that you have reductions in redundancies. If I'm going to use a piece of information like my address, I don't want to have to enter my address in 7 different places. I'd like to be able to just enter it once and have it stored in just one location so there's no redundancy of information. With an RDBMS, we refer to 2 pieces of information to describe the table structure. The cardinality is how many rows are there, how many actual records, and the degree of the table refers to how many individual attributes or columns are associated with that. If I have an ID number, a first name, a last name, and a job title, that is a degree of 4. There are 4 fields in that table, so that's the degree. What is the number of columns or the number of fields? If I have 20 people in my database, I have 20 records, my cardinality is 20, number of rows. So cardinality versus degree in an RDBMS. When you hear the phrase data warehouse, a data warehouse generally is designed to store and retrieve information quickly. However, it is not designed to change information quickly. It is a warehouse. It is a place to store things, not to use them on a day-to-day operational basis. You can change them. It just isn't designed for that. So a warehouse is generally a place you put data for archiving or for historical information that all you need to do is retrieve information for giving you analytics, but you don't need to use it on a day-to-day operational basis. When we talk about databases, we have to handle the transaction management. Every single piece of information changed in a database is changed in a transaction. Every transaction is separate. So if I want to change the value in database A to be 4, that is one transaction. If I want to take something from one database and give it, or one record and give it to another, that would be 2 transactions, removing from the first and giving to the second. 2 transactions because there are 2 different pieces of information that need to be changed. When we do transactions, sometimes it is important that all of the transactions in a group be run together. For example, if you want to create an invoice and you want to update your quantity on hand at the same time, create the invoice, then check your stock and see if it's on hand. If it's not on hand, I need to get rid of the invoice because I can't sell the item. Same concept of if I update my quantity on hand first and then create the invoice, well, if the guy can't pay for it, I need to put it back in the stock. So I need to undo the update to quantity on hand. There is no perfect answer of which one do you do first. So we need to be able to handle if there is a failure, everything needs to get rolled back. The same example with money. If I have $100 in my account and I want to give it to you, I'm going to take the $100 from my account, so remove it from my account, and then add it to your account. If your account is closed or locked, I can't put the money in your account. So now the $100 came out of my account, but it didn't go anywhere. Same concept if we first put it into your account first and then take it out of mine. If I don't have the money in my account to give it to you, we need to roll back the transaction. So transactions in database can be groups of statements, changes, each individual transaction that can be grouped together to allow us to do this rollback or commit. Once everything worked out nicely, we can commit. If there's any errors, we need to roll it back. There is an acronym in databases called ACID, which refers to the atomicity, the consistency, the isolation, and the durability of any group of transactions. The atomicity. Transactions must be all or nothing. They have to be either everything works or nothing did. You can't have them halfway. Consistency, all the rules must be the same before and after. This refers to primary keys and referential integrity. If my code deletes a foreign key or deletes a record somewhere, I need to make sure that all my foreign keys are still referentially integrity. So consistency makes sure that all the rules that existed before still exist after the transaction. Isolation means each transaction must be completed before the next transaction. This refers to changing code, changing the same data. So if I reference your record and I change your grade to an A, and then somebody else goes in at the same time and changes your grade to a B, which grade is in the database? You can't do that. You have to have one transaction was completed, the grade was changed to an A, then the second transaction happened and it was changed to a B, or it was changed to a B and then it was changed to an A, but they have to happen isolated so that each transaction can complete before the next transaction can be run. And finally, durability. Once the transaction is committed, it has to be preserved. We have to make sure that stuff doesn't change randomly or things that are in there don't happen where we put in a new data and then the data changes. There's a couple of things that we can do to ensure that our data is safe. There's a concept called database contamination, which is where I am able to access some data with a certain classification and you have a different classification, and we need to mix that data in the database with different classifications. This can be a problem. If you have different levels of access, you are risking data contamination. Who gets to see what? When I look in, I get to see all of your grades, but should you be able to see each other's grades? Well, no, obviously. So how do we make sure that the data exists, but individual people have different access? So a couple of options we have. Restricting access. We can say that certain users are not able to see certain tables at all. We can also limit views that say, if you are a student, you can view this piece of information, but you can't see this other piece of information. We can have user lockouts where certain users are locked out of individual tables. Then we go to the concept of concurrency. We can have updates that are lost, which would be bad, and we have what we call dirty reads. This is not inappropriate. Dirty reads are where we read something and we're using that data in our application, but somebody else has changed the data on the back end, and now those reads are old. They have old data and they don't have the new data. That can cause problems when we're changing pieces of information and somebody else has changed them out from underneath us and we don't know what the new stuff is. Another thing that we can do with databases is aggregation. Aggregation is being able to take a group of information and run aggregation functions, such as sum, count, average, min, or max. Take this group of data, who has the lowest grade, who has the highest grade, how many grades are there, what's the average grade, and what's the total of all the grades added together. Sum, count, average, min, or max. If I have the access to be able to do aggregation, I can use that information even though I'm not seeing individual records. If I think the book gives the example of if you are looking at military deployments and you see that there is only one group that is deployed in a specific location, and you know that John is in that group, then you know that the only group there is that group. That's a piece of information that you probably are not supposed to know. So being able to use aggregations to be able to get other pieces of information. If the count is only one, if the max is this, we know what the highest salary in the room is, so on and so forth. The concept of inference. Hackers use inference all the time. Being able to figure out something from the data given or the data not given. If I get that there is a zero count of deployments in this country, then I can infer from that there is nobody there. You can infer pieces of information by using database access. We use polyinstantiation to allow there to be different records for different classification. This goes with data contamination. So polyinstantiation, similar to polymorphism from object-oriented programming, polyinstantiation means multiple instances. We are creating multiple instances or different records with different classifications. If you are classification A, you can see somebody's date of birth. If you are classification B, you just see 000. So different values based on your individual classification. That's polyinstantiation, multiple instances of data. A couple of other things, we can limit our values. We can say that no salary can ever be over 300,000, so you can't go in there and just add an extra zero to your salary. We can give access to individual given tables, and we can actually break up our database into partitions and limit the access to those partitions in different actual data structures, hard drives, in different locations that are more secure. To connect to your database, we use ODBC, Open Database Connectivity. There's actually multiple different ways of connecting. ODBC is just one of the more common ones. The way ODBC works is it allows your front end of your full stack to be able to connect to the back end, which is going to allow you to use your ODBC manager to connect to your database. It provides access from the application through your database drivers to get to the actual data and then back. So your application, your full stack, at the server side is going to use some version of a database connectivity, so a DBC, either ODBC or JDBC if you're using Java, or .NET has different versions as well, to allow you to connect into your database and come back out. The full stack environment of front HTML, CSS, client side with JavaScript, going to the back end with your server, with your PHP or your .NET languages, and then back to your database and going back and forth. Full stack is how most web applications are built these days. Big data came out probably 20 years ago, 15 to 20 years ago. And about the same time, we realized that relational databases work great for lots of things, but they don't really work great for big data. Big data has three big V's associated with it. A huge volume of data, millions of transactions per day, a lot of them very fast, so the velocity is going really, really fast, and the variety. They are all different types of transactions. There's no real organization that we can do in a lot of the big data type situations. So we needed to create new things. We needed to evolve. We've taken relational databases that can no longer handle it and built new ways to handle it. NoSQL is not only SQL, it's an alternative to relational databases of tables and rows. We can use graph databases or object databases. We can use key value pairs. We can use document databases with XML and JSON. Different ways to store data that is not your standard relational database. If you are working in a large corporation and big data isn't really a problem, you will probably be using a relational database. If you are using Facebook, if you are dealing with any social media environment or anything that involves huge amounts of big data, you may need to understand these other relational databases or these other NoSQL databases, alternatives to relationals. Some of the security features are similar, some of the things we need to think about, but some are going to be different, and we don't have time to really get into those today. But those are things that you need to be aware of if that's going to be an environment that you have to work in. Our last section on databases is on storage threats. The data in a database is in a hard drive somewhere with lots of data on it. You need to be aware of all of the different ways to access the database. The DBMS goes through what we call the front door. They go through correctly, going through the front door like normal people are supposed to. But could you walk into the building that has the hard drive and pull the hard drive and get the data that way? Physically pull the drive. Could you access it through the network? Is the hard drive in the same location that's networked in with the rest of your network? Can you get to it from another location? If you are in cloud computing, can your data be accessed from another user within the same cloud? Are there different ways, directly or indirectly, to get into the shared storage media where your data is stored? As a security analyst, you need to understand all of the different ways to get in other than just the front door. There's the back door and the garage door and the windows and the data and the back basement and the attic and all the different ways that you can come in through to get into your database without just going through the front door. In our last section for this chapter, we're going to cover knowledge-based systems, including expert systems, machine learning, and neural networks. So, knowledge-based essentially refers to artificial intelligence. And I'm just going to kind of cover all three of these kind of in the expert systems, machine learning, and neural networks, all in the same kind of concept, because they all kind of go together. So an expert system, when we define those as far as programming, what we do is we give you a knowledge base. It is a series of if-then statements. If it is below 30 degrees, you might want to wear a hat and a sweater. If it is sunny out, you might want to wear shorts. If the temperature is above 100 degrees, you might want to stay home in the air conditioning. If-then statements. So a collection of all of the known information. And then the second part of an expert system is the inference engine. The inference engine is going to take all of that knowledge base and use it based on a series of inputs to determine the outcome. This is something that like banks use for determining whether or not you should be approved for a loan. We're going to take the collection of all of the known information. If your credit score is this high, if you have a tendency to be late on your payments, if you are this age, this gender, if you own these assets, if this, then you are a good risk, then you're a bad risk, whatever that happens to be. And then they'll come out with their yes or no. An expert system doesn't replace a person, but it gives a person a large amount of information to make a decision. So it will tell you with some degree of confidence whether or not this is a good or a bad decision. The purpose of an expert system is because the analytics of all of that information can make the program unbiased. Essentially, it's taking the information you gave it and inferring a result. Now, that doesn't mean that the knowledge you gave it wasn't biased. It's going to take that information. So the basis of an expert system is all based on that knowledge base. What is the collection of known knowledge that is used to make those decisions? That information is considered an expert system. Machine learning, on the other hand, refers to two different types of training for the program. The first is what we call supervised learning, or labeled training. We give you a series of inputs and tell you the output that was supposed to happen. So if I give you 2 plus 2, so the inputs are 2 and 2, you should give me back 4. That's the expected output. Go back and forth a few billion times, and the machine is going to learn, given this subset of inputs, this is the inferred output from that. Then we take it and we go to an unsupervised learning. Unsupervised learning does not give the machine the output. It gives it a series of inputs and asks it to figure it out independently. I refer to this one as the War Games example, 1980s movie with Matthew Broderick called War Games, where they had to teach the computer why thermonuclear war was a bad thing, starting him with playing tic-tac-toe. Why don't we play tic-tac-toe? Because once you learn all the rules, it should always be a scratch. It should always be a tie, because there's no point in playing. Given a subset of inputs, the machine learns on itself, unsupervised. You aren't telling it the output, it's determining the output and then saying, what is the modeling that needs to be created from that example? The last example of artificial intelligence is neural networks. We call this deep learning. And the theory behind neural networks is that we are expecting the computer to learn similar to biological reasoning that the human mind does, where it knows how to weigh the value of the input based on all the other knowledge that's already been given. The training for a neural network generally starts from the proper decision and works its way backwards through a series of tests to figure out how did I get to the conclusion, the appropriate conclusion from the subset of inputs. I give this one the example of the Weird Science with, again, 1980s movie of, I'm just going to give you a whole bunch of inputs and you're going to create the perfect woman for me. So it is not telling you ahead of time what the answer is. It is allowing you to biologically learn as you go along, given large amounts of data, given pieces of information from that, figuring out how to build the correct solution in the end. All three of these systems, definitely the machine learning and the neural networks, are huge right now, because being able to tell your computer how to come up with a solution in the end is great from a programming point of view. However, you always have to be aware of the security risks involved therein. What are the risks of giving machine learning, unsupervised learning, unlabeled training to figure out their model? What if they're wrong? And how do we make sure that the answer is not an answer that we don't want to hear? This chapter kind of ran through, how do you make software? How is software built? How do we, as security analysts, make sure that the data and the software itself is as secure as possible? We have to understand how the hackers access our data through the vulnerabilities in our software to be able to protect it. If there's a door to our house that we don't know to lock, how do we prevent people from coming through it? You have to understand the software development process to be able to understand how to secure yourself. Security should always be built in. We say built in instead of bolted on. Built in from the beginning. Ways that we can control that: process isolation, hardware segmentation, abstraction, and contractual arrangements. Contractual as in being able to have a contract with your providers and your vendors to make sure that you have guaranteed uptime. Abstraction, to be able to use modeling. Hardware segmentation, to be able to protect the data that exists on hardware. And process isolation, to be able to make sure that when we test things, we isolate processes as much as possible so that when we test them, we can be assured this process is safe, at least as safe as physically possible. Thank you guys for listening. Assignments are in D2L, so you'll be able to go in there. Please let me know if you have any questions, and have a wonderful day.